All right, hello and welcome back. We are live streaming on YouTube, and we do have a live Q&A going over on Piazza. So if you have questions, don't be afraid to put them up on either one of those. I am watching the chat as well. So today we're going to start on the actual material. Right? I just gave you a very quick introduction to what you need, what you saw yesterday in your lab, getting set up with your environment and stuff like that. And I also demonstrated the compiling, the writing, the programming, compiling, and running process. And of course, you saw that yesterday. What I want to do now is I want to go through that process again, but with a little bit more detail. Source files are plain text files, right? What we mean by a source file, it's just a bunch of text. It's not a Word document. It is not a HTML or anything like that. It's just a plain, what we call ASCII text document. It's a plain text document that contains computer code in a programming language at a high level. It's not something that a computer can understand at all. It is something that is meant for human consumption. It's not English by any means, but it's somewhere in between those two things. If we could program machines in plain English, I mean, that's Star Trek level kind of stuff. We're not there yet. So what we have to do is we have to compile that into an executable program. And the process for doing that is that you start out with the source, and there's actually a bunch of steps in between. Let me go ahead and give myself some more room here so that it always goes to the top. There we go. Also, let me know, I've turned it up this time, but let me know if you can't hear in the background. There we go. If you can't hear in the back, or you have trouble seeing and I just need to zoom in or anything like that. So anyway, there's a whole process that's going on behind the scenes. When I did gcc hello.c and produced that a.out file, there were actually several steps in that process. One of those steps was taking the source and compiling it to assembly code, and then taking that assembly code and assembling it into machine code, right? And there are a whole bunch of other things that are going on that I won't get into all of them, but I do want to show you basically what's going on behind the scenes a little bit, right? So we edit this source file, in this case hello.c, and this is the same exact program from last time. And if that one command, gcc hello.c, that did the entire thing in one shot. What I want to do is I want to show each one of those steps and to show you what it looks like. All right. What we can do is we can actually assemble this hello.c, right? And that'll produce this hello.s file. This is not something you'll normally do. I just want to show you what it looks like. All right. That is not C code anymore. It took my C code and it produced what's called assembly code. And it's even less English than the original, right? But it's still not something that a machine can directly understand. But you can kind of see what it's doing here. Subq, maybe subtraction, something like that. MOV, that's probably move something, right? It's a language that's closer to the actual hardware. The actual hardware has registers and memory addresses, and the commands are something like take this value and load it into register 1. Take this value and load it into register 2. Compare the value stored in register 1 to register 2, and if they're the same, jump to memory location 5. Right? Something that way back in the day when they started programming computers, they had to program in this language. Actually, they had to program directly in binary and have a bunch of punch cards, punch it for a 0, leave it for a 1, right? Thankfully, we don't have to do that anymore. That's why they introduced assembly language. That's why on top of that, they introduced yet another abstraction, high-level programming language like C. And today we have even more languages on top of that, like Python runs in an interpreter that was written in C itself. Right? So there's a whole bunch of scaffolding going on that takes us away from the mundane world of machine language closer and closer to English. Now, in the future, hopefully we can program but with plain old natural language, English, or whatever your natural language happens to be, right? Whatever your first language happens to be. Then what we can do is we can compile that, gcc hello.c, right? And again, that produces a different file called hello.o. The O stands for an object file. It's still not an executable file. If I tried to run this, hello.c, like I ran a.out, it wouldn't run because it's not a runnable file. All right. There's another process that it takes that code and it links it into a bunch of other machine code. In this case, remember that we brought in two libraries, standard library and the standard input-output library. Well, those are sitting somewhere on the system, right? Those have nothing to do with our program. Our program uses those as a library. So when I just compiled my my hello.c file and produced this object file right here, then it still was separate from those standard libraries. So the last step in the process is to link those in to those and grab the code, the machine code represented in those libraries, and actually build something that's executable. And that's what we did. Oops, that's what we did at the very beginning. GCC hello.c. It's taking all of those, each one of those step-by-step processes and producing immediately an executable file here. Right? What does that .o file look like? Well, first of all, it's not even going to, it's telling me that I can't even open it. But I can't, there are some tools that I can use. Hex dump, c hello.o. And that's what it looks like, right? It's just a bunch of numbers, right? A lot of those numbers are zeros, but it's incomprehensible to us as humans. It's something that the machine understands though, right? Okay, so I just wanted to show you that really quick demonstration here to show you the basics of what's going on behind the scene. Again, you'll probably want to use just GCC directly. When we get into libraries, you will want to use some linkage commands. You will want to use the compile command, but that's going to be later on. For now, all of your simple programs will simply just be GCC, that program, and it produces a new a.out file. Right? Let's see, I'm going to go ahead and close this and this and go back to our notes here. So if you want to, you can try it yourself and play around with these commands. I've put these into the notes. At the end of the day, when I post this to Canvas, you will see these notes also pushed out to GitHub. I'll provide the link to them. That doesn't mean that that doesn't abdicate your responsibility of taking your own notes. You should, because these aren't necessarily going to be complete. And again, the mere act of taking notes while you're watching a presentation helps you to keeps you focused, and it ensures that you have a higher chance of actually retaining that knowledge. Got a question online here. Okay, so I already answered that. These aren't slides. This is code, markdown code that you'll be able to find out in GitHub later on. Okay. All right. So we need something a little bit more substantial than that Hello World program. So what I've got here is a program that does a little bit more input and output. First of all, I've got my authorship header here. Who the author is, the date that I wrote this program, and then a little blurb to tell you what the purpose of the program is. By reading that in plain English, you already have a preview of what the purpose of this program is. What is it? It converts miles to kilometers. Okay? So now let's start going through line by line and looking at this stuff. And if this sentence was not there, do you think that we might be able to figure out by deduction, guess as to what the purpose of the program is? Let's find out. All right? So first of all, we're bringing in those two standard libraries again. The standard library has a bunch of stuff that's necessary for the language itself. The standard input, in fact, it's so standard that usually you don't even need this line. It's still best practice to keep that line in there. But usually the compiler sees it as such a necessity that it just brings it in automatically without you telling it. The standard input-output library, that has a bunch of input and output functions that we can use. This is called a preprocessor directive that we'll get to in a second here. But what do you think? What do you think that number there is for representing? Yeah, go ahead. Yeah, there's 1.60934 kilometers in 1 mile. How did you know that? All right, if I just had this number, would you immediately say, "Oh, okay, that's the number. That's the number of kilometers in a mile"? Right? How many people have that committed to memory? Not many. But by reading KMS per mile, you have an understanding of what that number means, right? You have a very good, this is not a variable technically, but you have a very good idea because we've used good English names for these things, good descriptive names. We've got that same main right there. Every runnable executable programmer, or every executable program has a main entry point. Every program has to start somewhere. In C and most programming languages, that starting point is the main. Don't worry about these. These are command line arguments. We'll get to those later. Right? Now I've got some variables here, and if you've been doing your reading, you've seen this kind of variable declaration. I've created two what are called double variables. Double variables are simply just floating point numbers, which are called fractions, 3.5 or 3.14 or 0 or 5.0. Right? Those are all floating. Those are all double numbers. Alternatively, there are integers, which are whole numbers. There are chars, and then there are a couple of others that we'll get to later on in the semester. Right? All right, what are these two lines right here? Well, first of all, what's this line on line 16? What's that doing? That's telling you what it does, right? It's a comment, right? Documentation is super important. Now, in a real program, this is just basically our second program. So in a real program, I would never put in a comment like this because code should be self-documenting. Anybody who has done C for even a week will know that the printf function prompts the user for an input or prints something to the standard output. That kind of documentation is not necessary, but I put it in here so that I can show you the syntax. That's a comment, and are those slashes or are those backslashes? They're slashes, also called forward slashes. How can you tell the difference? Stand to your right, and are you leaning forward or are you leaning back? Right? This is a backslash, that's a forward slash, or just slash. Right? It prints this message to the user. Please enter miles. Right? And then we read the input from the user using scanf. So printf for input, printf for output, scanf for input. We'll talk about this momentarily, but it's magic for now. Right? Likewise, this ampersand is magic for now. Right? We'll demystify that magic later on. KMS is equal to KMS per mile times miles. So you can kind of tell that if the user enters, say, 10 miles, right, then what will the value of KMS end up being? It'll be the number of kilometers in a mile times 10 miles, so about 16.09 kilometers, right? How is that computed? With a star. What does that star stand for? What do you think? Multiplication, right? Do you see anywhere on your keyboard that has the multiplication symbol that you're familiar with, right? Nope, the standard QWERTY keyboard is over 100 years old or so, and they never thought to put in multiplication as a symbol on the standard QWERTY keyboard. Whether or not it's the X or the dot or just in general, right? Normally you would put AB without putting anything in between. You can't do that with code. You have to be explicit about your operations. Right? So star kind of looks like that multiplication, so that's going to be our symbol for multiplication. Right? Plus, minus, those are on the keyboard, right? So we can just use those. Plus symbol and then the hyphen for minus. What about division? Slash. And again, is that a forward slash or a backslash? Forward slash, good. All right. And then we print a message out. %F, I don't know what that is yet. It's a placeholder. Miles is equal to blank kilometers, and we end up printing miles and kilometers. So we kind of have an idea of what this program does just by reading it line by line, even if we knew nothing about coding at all. Right? But of course you do because you've started on your reading already, which is due Monday. But even if you didn't know anything about coding, you read this, well, you kind of get the idea of what this program does. In fact, if we run it, if we compile it first and then run it, it prompts us to enter miles. I don't know. How much is a marathon? 26.2, right? That's equal to 42 kilometers. Right? I've never done a marathon, but I've done a half marathon, which is going to be 13.1. That's 21 kilometers. Right? Okay. And again, if you're Like it was posted in Bits and Bytes. If you want to, you can come out and run with faculty. Bonita and I will be running a 5K on the 3rd at 9 a.m. if you want to come to the Shore Center and run with us. All right, so that's, I mean, just by reading this line by line, you can kind of get an idea of what this program does. And that's because programming languages are as close to English without getting there as possible, are made to be that, are made to be understandable to humans. The very fact that we started at the top of this file, read left to right, top to bottom, right? That tells you how a program operates. If I've got command, 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 then it goes in that order. It doesn't just jump all over the place. It doesn't go backwards or anything like that. It's close to, well, it's close to English, and so it's read top to bottom, left to right, unless you do something that changes that sequential behavior. That's called, if you got command 1, 2, 3, it goes in that sequence, 1, 2, 3. Right? Okay, so what I'm going to do is I'm going to make sure that this is in the notes for you. And again, when I post this, you'll see this when I post this to GitHub. It'll look a little bit different. I've got a dark theme here, but whatever. So let's go back over that, and let's talk about each individual element. Right? So where did we start with? We started with these comments. Right? So comments, all right, it's not snapping. There we go. Comments are human readable messages embedded in code. Right? And we saw two different types of comments. One are single line comments. Begin with a // Remember that is a // two of them, right? And anything following on the same line is ignored by the compiler. In fact, it doesn't even end up in the compiled code. All of your comments, it might even be the preprocessor, I'm not sure. It goes through, looks at all the comments, throws them out immediately because it's not going to do anything with those comments. They're intended for human consumption, not for the machine. Right? You also have multi-line comments. Multi-line comments begin with a, what did it begin with? /* and end with a */. Right? Anything that you put between them is ignored. Anything in between is ignored. And consequently, if you don't end it, right? Oops, I forgot to end that multi-line comment. What happened to all the code syntax highlighting here? It's all grayed out now, right? And is this something that's compilable anymore? No. Nope. Error. Unterminated comment. Right? It's the compilers are getting better. They're getting better and more helpful in their, something went wrong. Oh, here's probably what went wrong, right? You never ended that comment. And not only that, but it's telling you where it started. This is, not that. This is line number 1, column number 1. And if I jump up there, I can see that that's where the comment started. Of course, it's not going to be able to guess where you intended for it to end. So you're going to have to go back and, I intended for it to end right here. Right? Now, why did I put why did I put 2 stars and then a whole bunch of vertical stars? That's what's called a doc style comment, documentation style comment. Right? So doc style comments, or style, excuse me, are multi-line comments that have a /* and a vertical line of stars. All right. They are intended to provide full documentation on a program or function, etc. Right? And they're used to provide documentation. And the reason we use that kind of setup is because it's actually a whole nother language itself, the documentation language, where you can annotate things, you can mark it up with, say, HTML code, so that when you go to compile your code into an executable program, that's one thing, but you also want to produce documentation for other people so that they know how to use your program or use your code. And you can run this through a doc parser, and it'll produce this very nice, HTMLized code that you can then publish on the web or something like that. Okay. You should get into the habit of using docstyle comments. As far as the rubric is concerned, for all of your programs, you will need documentation on all programs. All we're looking for is in the first couple is authorship documentation, just like I have here, right? Who wrote it, what the date was that you wrote it, and what does the program do. Later on, when we get into more sophisticated and complicated code, you're going to want to document every single function that you write. Okay? All right. Comments, especially documentation, is intended for the user, right? It's intended for human consumption. It's intended to tell the user the what, or the why, and the how, not the what. Anybody who is competent at programming at that particular language, which you will be by the end of this course, maybe not necessarily yet, but you will be, right? Should be able to read the code and see that it's self-documenting. And that's what I mentioned before. You should know by the end of the week, end of next week certainly, you should know what the printf function does. It prints something to the standard output. You should know what the scanf function does. It scans from the standard input, right? This kind of documentation is superfluous, unnecessary. In fact, we call it cruft, C-R-U-F-T. So I'll try to share as much slang and lingo as possible as we go along here. Cruft comes from either Harvard or Stanford or something like that. Their computer science department, or some department on campus, had on campus there was a building called Cruft Hall. And Cruft Hall was not used for any classes or anything like that. And so what happened is it started to become the junkyard. Oh, we've got an overhead projector that's broken. I'll throw it into Cruft Hall. We've got a bunch of file cabinets going back 50 years, stuff that nobody ever looks at, but we can't get rid of it because we might need it, so throw it into Cruft Hall, right? Eventually, Cruft Hall filled up with garbage, or unused stuff that was just clutter. That's what cruft means in the context of code. It's clutter. These these kind of comments are clutter. They're cruft. We don't want them in practice. I'm only putting it here because I want to show you what they look like. Okay. Otherwise, code should be self-documenting. Code should tell you the what. And you should be able to read the code, and as long as you know the programming language, as long as you're familiar with the with the syntax of that language, you should understand what it does. Right? The why and the how, that's where that's where those documentation, real documentation comes in. Okay. All right. What's next? Well, of course, we've got these three things. These all begin with a hash. A hash is what's called a preprocessor directive. So preprocessor directives. All right, it's still not snapping. I'll have to fix that later. Are directives to the compiler to do something before it compiles, right? Before it starts compiling. There are several different types of preprocessor directives. We're only going to look at the two that I just showed you. You can use the syntax include to bring in an external library, right? That provides a bunch of useful functions that you can use, right? So we've already seen two of them already, stdio and stdlib. Those are very useful because if you don't have input-output, maybe your program doesn't do anything at all. What else might be useful? What if I wanted to compute the square root of something? Right? So you pick up your calculator and there's a square root button, right? It would be nice if we could do something like that in code as well. What library do you think that we should bring in then? Yeah. Math, right? So here's another example. Include math.h. Note the syntax here. We use hash include, no space. We then put a space. That space is actually optional because generally white space doesn't matter in code in most programming languages, but we are going to use that style here. And then you use the, less than and the greater than sign. In this context, here's some more lingo. We call those Langle-Wrangle. Why? Left angle bracket, right angle bracket. Langle-Wrangle, right, for short. And then we put inside the name of the library that we want to include, the name of the library that we want to bring in. Generally, libraries end with a .h, right? You only want to bring in, that H stands for a header file. We'll understand that later, probably in week 5 or so. But for now, you know that all the libraries that we brought in so far follow the same exact pattern. Standard lib.h, stdio.h, math.h. Right? We'll be bringing in more libraries throughout the semester, and you'll be creating your own libraries as well. Again, probably in week 5. All right? You can also use macros, right? Using the define directive. Right? Macros are a basic cut and paste, replace operation. Right? So I'm going to go back over to my code here and let's take a closer look. What this preprocessor directive does is says, anytime that I use in my program KMS underscore per underscore mile, before you compile, replace that with this number. Right? Think about a program here where I just used that number directly. I didn't do a preprocessor directive. I just had this mysterious number. Right? If you looked at that code, of course you could probably tell what it does by the context of everything else and the fact that I'm using a variable called miles and a variable called KMS. Right? You could probably say, oh, well, that's probably going to be the number of kilometers per mile, right? But is that all that satisfying? No. Now, certain numbers you do immediately off the top of your head know what they are. If I were to write 3.14159, what would you immediately come to mind? Pi, exactly. 2.753, or whatever it is, 2.735 something, what is it? Yeah, E, okay, far fewer people answered that one though. What if I came up with, I don't know, now I can't even think of it, 0.6372 or something like that. That's the golden ratio. Of course, everybody knows that, right? No, the point here is that these are called magic numbers, right? Simply putting a number into a program, that means it's this mysterious magic number. Where the hell did that come from, right? You want to make your code readable to other people. The only way that this is readable is if you use a human readable and understandable term for it. That's why we use these preprocessor directives. Anytime that I have this, and it's not a variable, but anytime I have this label, I want you to replace that with the number above. So one, it provides an immediate way for somebody reading this program to understand it. The second reason that you would want to use something like this is how many, it's not that accurate. 1.60934, I mean, that's accurate enough for anything that we'll probably want to do. But you can have more sig figs, right? What are sig figs? Significant figures, right? Does anybody know the next number in the sequence? No? Okay, I don't know either. But for example, define. What if I define my own pi here to 3.14? That's kind of accurate, but what's even better? 159, and now does anybody know any of the other digits? Okay, blah, 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 who cares? All right, but the point here is that if I use a if I use just this mysterious magic number 50 times throughout my program, and I wanted to change it to be more accurate, I would have to go to all 50 of those locations and change every single instance. Not only that, but then I have inconsistencies. Maybe it's 3.14 in one place, and it's 3.14159 in another place. I'm going to get different figures every single time. But if it's in one place, and I want to make a change, I have to make one change, and that change is affected to all other places. Right? Now, don't define your own pi. The math library defines pi for you. Right? In fact, it defines a pi called m_pi. Right? And all you have to do is bring in the math library, and you've got that automatically. Right? What do you think the M stands for? Maths pi. So if you really do want to define your own pi, you can go ahead and do that, and there won't be a conflict. But don't do that. Use the math library's pi if you ever need to. Right? Okay. So macros are a basic cut and paste operation. They allow you to give a human readable term to mysterious magic numbers. They allow you to have one single change, or it allows you to only have to make one single change to change all instances of that value, right? So two great advantages right there, right? Keeps it in one place. What's the next part of this program? The main, right? The main entry point. The main is always the starting point for any executable program. Go back over here, right? And come back out. Sorry, there we go. There. For now, argc and argv are magic. All right. Again, we're not going to get into explaining them until we get to command line arguments, but they are command line arguments. You can provide input to your program from the command line when you run it. When I go a.out, I can immediately provide non-interactive input to my program rather than the program going, hey, human, I know that you're sitting there. Can you go ahead and please enter the number of kilometers that you're trying to convert, right? And then, okay, here's the result, right? And that's interactive because the program is prompting you for something and then sitting there and waiting. An alternative is non-interactive input, where I can just go ahead and immediately enter it when I invoke the program, and then it doesn't sit there and ask me, okay, human, go ahead and mash the keyboard for me, right? And it's a little bit better because, of course, we like automated processes, okay? What else do you see here? Think English. Right? Again, we want our programming languages to look as much as like natural language English as possible. So what parallels do you see between this and, say, an English paper? Yeah. Oh, yes, right. We'll get to variable types later. But think about punctuation. Think about grammar. Think about that kind of stuff. Yeah. Excellent. In natural language, at least in English, how do we end a sentence? Period, right? In programming, we use semicolons. Semicolons end every executable statement. Not every line, not every, because not everything is a sentence, but it ends every executable statement. These are executable statements. Create these two variables for me, please. Period. Print this out to the standard output for me, please. Period. Read in this from the input, please. Period. Right? Except that it doesn't use a period; it uses a semicolon. Right? The vast majority of programming languages borrow this from C. This is C-style syntax. If you look at C++, C#, Java, PHP, a whole bunch of other things, they all use semicolons to end an executable statement. It's punctuation. Right? Yep. Oh, sure, go ahead. All right. What else do you see? Again, think punctuation for now. Yeah. Oh, okay. Parentheses and curly brackets. What's that analogous to? Maybe in plain old English. If I've got executable statement, executable statement, executable statement, and each one of those is kind of like a sentence, then if I've got multiple sentences, what does that make? A paragraph, right? So blocks of code are denoted using opening and closing curly brackets. Right? And that basically sequesters that piece of code by itself. Those are logical units of code. When we go and write functions in a couple of weeks, we will sequester those functions in opening and closing curly brackets. Right? It collects all of those executable statements, all those sentences together into one logical paragraph, right? Or one logical block of code is what we call it. What else? Yeah, go ahead. Commas, right? What are commas used for? What are commas used for in English? Separators, delimiters. Commas delimit lists of similar things, right? So we see up here, I want to declare two variables, one called miles, one called KMS. Right? If I just had a space here, would you write it like that in English? No. It's a list. And if you've got multiple things, foo, bar, baz, right? Oops. That last comma in English is called a what? Or I guess if I wrote it like this, that last comma is called, this last comma would be called an Oxford comma, right? We don't have any such thing, right? It's just comma, 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 comma. There's no trailing comma or anything like that. There's no keyword and, by the way, in C either, right? Any question? So, say again?
I think I prefer to see them in there.
Okay, what?
I think for the quotation marks.
Oh, quotes, right? Quotes, that is, quote, double quotes, I'll say. Double quotes denote strings. Strings are sequences of characters. So now let's bring it all together. Characters form words. Words form sentences. Sentences form paragraphs. In this sense, strings are single characters. For example, the capital P, lowercase l, lowercase e, dot, dot, et cetera, et cetera. And it opens with a double quote. It ends with a double quote. Anything in between that is treated as one thing, one string, one statement. You cannot use single quotes. Single quotes are, and you can see here the syntax highlighting is completely different. In fact, it's going to be completely invalid. Double quotes are for strings. Single quotes are for single characters. Right? We'll talk about that when we get to other variables. All right. What else do you see? Oh, let's go back over here. Anything? The ampersand. Magic for now. Yes, that is punctuation. What that is, if you really want to know, is it's a pass by reference. What we're doing is we're getting the memory address of that variable instead of the variable itself, so that we can make changes to that variable in the function. Right? We're passing it by reference rather than passing it by value. We'll talk all about that in week 5 or so. Right? So don't worry about it for now. Understand, though, anytime you see scanf, you need that ampersand. If you don't, hopefully the compiler will be nice about it and tell you, yeah, you can't do that. KMS per mile, there we go. Yep. Warning, format LF expects an argument of type double, but the argument 2 is of type double, right? And so there's this star versus this, this double star versus this double, and it's telling you that there's something wrong here. It's not telling you that, hey, you should have put an ampersand there, right? But that's the implication, right? Okay? So I'll hold off on that one until next time. What else? White space, in general, does not matter. Right? So for example, I could go ahead and put in a whole bunch of spaces here, a tab. I could tab over a bunch of more spaces here, and then I could put spaces at the end. Right? That's not going to matter. That's going to compile, and that's going to run just as it did before. Right? That's not going to have any impact on the running of the program. Generally, white space doesn't. Now, if white space inside of strings certainly matters, because one space versus two spaces, that's different. But in the code itself, it doesn't matter, generally. Now, which did you prefer? The original, where I didn't have a bunch of superfluous white space, or what I did here and mashed the keyboard, mashed at least the space key? The original, probably. Why do you prefer it like this? It's much more readable, right? And again, one of the things that you want to do is make sure that your code is readable. This is good style, right? What other kind of white space do you see here? Tabs, right? In fact, I didn't use tabs. I'm using 2 spaces, but you can use tabs. You can use 3 spaces. In fact, there's a study done on GitHub. What's the most common 2 spaces, tabs, or 3 spaces, or 4 spaces, or something like that? I think, don't quote me on it, but I think that the 2 spaces won. Or no, maybe it was just a study of, do you prefer spaces or do you prefer tabs? And I think that spaces won out, right? The key here is to be consistent. Do you see how every single line here is indented by 2 spaces, it's not all over the place, right? Maybe don't indent anything. Maybe indent just 1 space on another. Maybe indent all the way over here so that it's no longer even viewable on the same screen anymore. Good idea, bad idea? Bad idea. Think about think about the English paper. Think about not the essay itself. Well, yeah, you could think about the essay too. What begins every single paragraph to tell you that that's a paragraph? An indentation. Or if you go with paragraph, then a single space, then paragraph, single space, paragraph, right? It makes it a lot more readable. A novel, of course, will just have indentation at the beginning of every paragraph. If you don't have that, it just looks like one big giant wall of text, which is very, very hard on the eyes, very, very difficult to read. Right? Now think about an English paper where you've got an outline. What does that outline look like? Topic 1, topic 2, topic 3. Topic 1, subtopic A. What do? In your outline, you indent. Subtopic 1A or 1A2, right? And then little Roman numeral 2 instead, right? You're indenting at each logical level. So code blocks inside of code blocks inside of code blocks should all be indented and should be all at the same level. Now, there's only one code block here for this example because it's such a simple program. But I begin my function here with this opening curly bracket. I make sure to indent every single line in that function, and I make sure that they are all vertically aligned. And I'm making it a little bit more readable by putting in some nice little white space in between each one. Right? Not absolutely necessary, but you can use blank lines to denote this is a major piece of code, and then this is the next major piece of code, and this is the next major piece of code. You don't have to double space everything, absolutely everything, right? Just make it so that it's readable. Okay. So, good styling. All right. Let me go back to my notes here. There we go. All right, there we go. Use horizontal white space when appropriate. Use vertical white space when appropriate. Use indentation to indicate blocks of code. Variation on style is okay, right? As long as you are consistent about it. It doesn't really matter because if you're writing code for an organization, like you go to Microsoft and you start writing C code there, they will have what's called a style guide. And you are forced to use their style guide to make sure that their millions and millions of lines of code all match up with style. You go over to Google and they'll have a slightly different style guide. It's just that now you have to follow their style guide and just be consistent about it. Adopt a style that makes sense, stick with it, and be consistent about it. You shouldn't be all over the map with your white space. Right? In fact, if you want to, you can usually find a styler, like for example, if I won't open it right now, but on Canvas in the extra resources, there's some websites that you can do that you can take your code, put it into that website, and then style it in different style, like Google style or GNU style or something like that. It'll reformat the code, then you can go ahead and copy that back. It'll automatically take care of all that stuff for you. All right? In fact, there is a nice tool that you can use in the CS50 IDE. Hopefully it's still there. Which A style? Yep, good. All right, so let me really screw this up. Bunch of bad white space everywhere. Oops, not that though. That's a completely different program. Tab, tab, tab. Right? So we're all over the place here. Let me go ahead and fix it using A style on KMS2 miles. Ooh, do you see what it did? Well, not exactly 100%, but it did change it so that it was a little bit more consistent. It at least made the vertical alignment of all of these lines correct. Right? So space, 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 tab, tab, tab. Let's save it. A style. It fixed it all for me. So if you want to, first of all, you should get into the habit of writing it well the first time. When you write an English paper, you don't sit there and write with no sentences whatsoever, right? And then you go back, oh, okay, I'll go back now and separate all the sentences out. I guess if it's like an insane, word dump, yeah, maybe you do that. But you don't do that. Generally, you don't do that in good English essays. you certainly shouldn't do that in good programs. You should get into the habit of writing good style to begin with, not relying on tools like ASCII. But at the very beginning, of course, if you need, what does good style look like? Go ahead and run ASCII and see how would it format it a little bit differently. Right? Okay. There we go. So I'll put that in the notes just to remind you. You can use style format or formatters. Sometimes these are called beautifiers or prettifiers. Prettifier, that's not a word. In computer science, we like making up words a lot. So there's no such word as prettifier, but what does it do? What do you think? Makes it pretty, right? So prettifiers to format your code, right? For example, the one we just used was ASCII. If you want to use a website, take a look at the resources on Canvas because they've got like a website where you can put your code into one place, format it in any number of formats, and you can see what the differences are between Google style and GNU style and Microsoft style or whatever. Right? What else do you see here as far as words go? Now, I will call your attention to these words. Int, char, double, all the purpley stuff, right? Return. Those are all key words or reserved words, right? So certain words are reserved by the language itself. Right? For example, double, int, return, etc. And have a very well defined meaning to the language. And you cannot, or should not, in a lot of cases, change their meaning. So, for example, I created a couple of variables here, right? I created a variable called miles. I created a variable called KMS. Would I be able to create a variable called return? No, it's purple. You can't do that, right? Because it's purple, right? No. It's because it's reserved by the language. You are not allowed to use that as a variable name, right? So we won't use that as a variable name, okay? So let's talk about variables though. C is what's known as a statically typed language. Don't worry about the technical details of what that means. The basics are that you have to declare a variable, and it's both its name and its type before you can use it. The name of a variable is its identifier, and the type is the type of value it holds. Right, we'll talk about types here in a second. But before we do that, what the hell is a variable to begin with? Think math. What's a variable? Usually you think of it in terms of like x, right? Yeah. It's a placeholder name for a value. If I say f of x, x is like an input value, right? F of x is equal to x squared. If I put 2 as the value in that, then the function becomes 4, right? 2 squared is 4. If I put 3 in there, then it becomes 9, right? That's a variable. Or another instance would be a squared plus b squared plus c squared, or a squared plus ax squared plus bx plus c is equal to 0. All those coefficients, those are variables. I don't know what the value is. I want to talk about them abstractly. Likewise, the variables over here, miles, that could be any value that the user mashes their keyboard on, right? It could be 5 on one run of the program. It could be 10 on another run of the program. The variable varies its value. That's why we call them variable. They vary, right? The name of the variable is its identifier. The type of the variable is its type. And we use the type and then the name. If you have multiple variables of the same type, you can use this common delimited list here. So let's first of all talk about types, and then we'll talk about names. But first, let me reiterate what I already wrote. You have to declare them before you can use them. Let me move this down here. Right? Is this going to compile anymore? No. I used miles up here before I declared it. Right? Each undeclared identifier is reported only once. The compiler is saying, I got to line 19 and I'm seeing a variable here called miles. I never saw that before. I don't know what the hell you're talking about. Right? You need to declare this variable before you actually use it. Now you can separate your variable declarations and say, all right, well, I need to use miles, so I'll go ahead and declare it, then use it. Oh, now I need to use kilometers, so I'll go ahead and declare it right here. Right? You can separate your variable declarations, but is that as nice? No. First of all, it leads to superfluous lines. Second of all, it doesn't collect all of your variables in one place. KMS. What happens if I leave that? Let's find out. It's not an undeclared variable declaration. What is it? It's previous declaration. Can you declare two variables with the same name? No. Just like no. When you post to Piazza, in fact, when you enroll in Piazza, make sure that you're using your full name when you sign up, because if your name is John, we have 250 folks, 220 people in this course, and guess what? There are 3 or 4 Johns, right? So make sure that you're disambiguating that, because if you post, I have a problem with my code, can you check it out? John. Okay, well, we don't know who there are 5 Johns here, which one are you, right? So you need to disambiguate these things by having separate variable names, having a separate name. Even if you do have like John Smith and John Smith, you're still uniquely identified by your NUID or something like that, right? All right, so can't have variables of the same name in the same scope, and we'll talk about scope later on, okay? Now, what about types, variable types? We're only going to look at, there are several variable types throughout the language. In fact, you can define your own variable types, which we'll do by the end of the semester. But we're only going to start with the 3 basics. First of all, an int. What do you think that's short for? An integer. An integer. Now, here's the technical details. It's a 32-bit signed 2's complement integer. Ignore that, right? Understand the implications of what that means. It can represent whole values, integers, in the range. And for this, I'm just simply going to cut and paste it because it's LaTeX, which is a typesetting system used for mathematics. That's how I'm getting those nice less than or equal to signs there. You don't see that anywhere on your keyboard, right? I have to use special symbols to get that. So this is 2.147 billion and some change negative. It can include 0, right? So you can represent 0. You can represent 1, 2, 3, 4, 5, all the way up to 2.147 billion and some change, right? What happens if you have a number that is larger than that, right? What if you had 5 billion? Or how many people are on the planet now? 11 billion or so? Can we represent that here? No, right? That's too big. The number of negative people on the planet, negative 11 billion. Can we do that? No, no. There are built-in limits and constraints on the types that you use here. So what happens when you have a need for a number that is larger, an integer value that is larger than 2.147 billion? You're going to bring in a library to do it. That goes beyond the scope of this course. Right? Don't worry about it. Right? We'll talk about the implications of that here in a little bit, though. Right? A double. It has nothing to do with floating. There are floats in this language if you've ever seen any other languages, but we're not going to cover those. They're ignored because we like doubles because they are double precision numbers. They're floating point numbers. And again, if you want to know what that means, it's an IEEE 754 floating point number. Forget about that. Right? Just know that it represents a decimal number that has about 16 to 17 digits of accuracy. Okay? So you can represent pi out to 16 digits. If you want to represent pi out to 5,000 digits, it ain't going to happen, at least with any precision. Right? There are limitations on the representations of numbers in a computer. Pi, for example, 3.1415, blah, 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 blah. Does it ever end? Does it ever repeat? Nope. You cannot represent pi exactly in a computer because a pi has an infinite representation. A computer is finite. As many of you know, you eventually run out of memory, right? And then you need to download more RAM, right? Yeah, go ahead. It's based on the standard. It's an IEEE standard, 754. IEEE is, it's an acronym for electrical engineers, something, I don't know what it is. But it's an IEEE standard that dictates exactly how they behave, exactly how they're represented. It's basically scientific notation. You have a sign, plus or minus. Then you have a number that is normalized so that 3.1415, right? It's a number between 0 and 10. And then you have what's called, that's the mantissa. And then what you have is an exponent. If you want to shift that period somewhere, right, then you multiply by 10, some power of 10. Right? Same idea, but it's all in binary, which we're not going to really get into in detail here. Right? So instead of multiplying by 10, you'd multiply by some power of 2 because it's binary. Right? And then finally, a char, a single ASCII text value. So already we're getting into the alphabet soup here. ASCII is the American Standard Character in I something, right? Let's find out. ASCII. ASCII is American Standard Code for Information Exchange, Interchange. It's actually pretty old. It dates back, I believe, to the Eisenhower administration. They're the ones that standardized this. And so that's why there's that A in there, American, right? Because Americans were on the forefront. You can argue that Americans were on the forefront of computers during the Cold War, the very beginnings of the Cold War, and so they established this standard. I don't know if there was, the Brits certainly were deep into computing, but I don't know if they established their own character set or whatever. But you needed a standard, right? If you've got an electronic standard, A through Z, and capital A through Z, and exclamation point and question mark, right? We need a standard to dictate what those things look like. And so that's that started out, again, in the late 40s or 50s or something like that, as the ASCII code. Right? And once this is loaded up here, we can see what it looks like. For example, come on. All right, fine. ASCII table then. There we go. That's a little bit easier on the eyes. Well, it's not so easy on the eyes, but there we go. So capital A is represented by a number, in this case, 65. So it starts at 0, so the 66th character corresponds to a capital A. 97 corresponds to lowercase a. And you notice here that they're in order, A, B, C, D, E, F, G, ... Right? Capital letters come before lowercase letters. And then we've also got a bunch of punctuation, right? That an ampersand comes right after the percent sign. These were all set up in this table so that you have these nice operations. To convert from a capital letter to a lowercase letter means that you only have to flip one bit in the binary representation, right? There was a rhyme and a reason for this thing to be put together in the 40s and 50s, right? We've also got, these control characters. For example, remember that we went to the end of the line when we did the Hello World program? /n. That's a special control character that says go down to the next line. Where is that over here? I think it's, 10. NL, that's line feed. You might see /r sometimes as the next line. That's called a carriage return. I forget which one that is. There we go. Carriage return, 13. And why? Because, again, this was done in the 40s and 50s. We didn't have nice keyboards back. We had QWERTY keyboards back then, but they weren't called keyboards. What were they called? Typewriters. There is a difference on a typewriter. If you get type, ting, 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 and then you get to the end of the line and it goes ding, right? Does it do anything? No. what you can do is you can push it all the way over to the back. You've seen this in movies and stuff, right? Like type, 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 ding, and then they had to manually push it back. That went to the that went back to the first column and then went down to the next line so you could continue typing. You could also take the drum and simply just turn it. That's the difference between those two things. A new line goes to the next line and goes all the way back to the beginning, chink, right? And the carriage return simply just goes and turns the drum down to the next line. Right? So there's stuff that we're dealing with from, well, I guess now over 70 years ago, still in our standards. Nowadays, we need more characters, right? Again, as the A implies, this is very American-centric, right? This is very English-centric. Would we be able to typeset, say, what are called CJK fonts? Chinese, Japanese, Korean fonts. Do you see them here? Nope. And most recently, or what about Egyptian hieroglyphics? Those are standardized. What about the things that you put on your texts? What are those called? Emojis, right? We now have a much larger Unicode standard, right? Unicode, over here, it only uses 1 byte, so we only have 128 possibilities. And then we have an extended ASCII character set with the Cyrillic fonts and stuff like that, like an umlaut, right? So, because the Germans wanted to get in on the action or something like that. And so we extended it, all right, fine, not just American, but we'll extend that so that we've got some Cyrillic and stuff, and diacritics. Well, that wasn't enough. We also need, foreign languages, non-English languages. We need dead languages like Egyptian hieroglyphics. We need made-up languages like Klingon. And by the way, the Klingon was proposed to be added to the Unicode character set. It was rejected because it was a made-up language, right? But emojis, right? Yeah. What else do we call them? Emoticons, et cetera, et cetera. Those were ultimately standardized in Unicode. And so that you can have a smiling Unicode face, whatever. What is it called? Unicode, emoticons, smiling face emoji, right? There it is. And it has a code. Where's its hex code? Hex. There we go. It's number 263A, right? Remember, everything in the ASCII text table here has a number associated with it. A hexadecimal number is base 16, 0 through 9, and then also A through F. And this smiling emoji here is 263A, right? So several million or several thousand characters into the Unicode standard, we can have this smiling emoji now, right? So that's Unicode. Don't worry about Unicode. Only worry about ASCII. Right? You can't, in fact, it's very difficult, at least with the setup that we have here for to get full Unicode support in C. You don't want it anyway, right? What would it look like if I had a variable named after this thing? Right? Let's copy it. I don't even know if you can do this in CS50. Let's find out. Int. There we go. 123. Is that a good idea for variable names? In fact, I don't think it'll even compile. Let's find out though. Oops. Where am I? All right, it reset. I need to go into main, gcc, hello, hello.c. Yeah, it's not gonna. It doesn't know what the hell you're talking about. So don't do that. It's bad. Some languages do support this, and there are probably ways to get C to support this. I know that Java you can use characters, but even in other countries like say Japan, they will not use Japanese fonts to denote their characters. Usually, they'll use plain old ASCII text because it's far more interoperable than Unicode is. Right? So don't do that. But know that it's just an extension. We started out with the basic American standard code interchange, whatever. We extended it. We extended it, and now we've got full Unicode, which I think supports over 1.7 million different characters. And most of them are not taken, so we have plenty of room to grow, right, for any new languages that come along. Right? All right. So those are the types. Declarations. You declare a variable by providing by specifying, I should say, its type and its name. Right? Its name, or identifier, has to follow rules. Right? For example, you cannot begin a variable name with a number. You can have numbers in your variable names, but you should not. You can have numbers, but you shouldn't. Because then you get into a bad habit. Variable 1, I need another variable. Variable 2, I need another number. Variable 3, don't do that, right? You should name variables after what they represent, right? So for example, KMS, kilometers, miles, obviously does what it says in the box, right? It's miles, it represents miles. Now the one exception to this is if you're doing pure math. You know, mathematicians aren't that creative. They create a variable and then what do they call it? X, Y, Z, A, B, C, right? They're not that creative. Well, what does that represent? I don't know, it's just math, right? Well, ultimately your math is modeling something, right? So when we go to actually code this stuff, let's name variables after what they represent, not just some mysterious X, right? You should name variables after what they represent. Avoid abbreviations in general, right? Of course, I abbreviated over here. And that's okay, why? Because in the context, if you're talking about miles, what must KMS stand for? Kilometers. If you want to, go ahead and go with a pure naming system, kilometers, right? And I'd argue that that's even better, right? But if it's understandable from the context, then you can use abbreviations and acronyms. Avoid abbreviations and acronyms unless they are absolutely clear from the context. Your variables may contain characters A through Z, lowercase. In fact, I'll typeset this. A to Z, uppercase, 0 through 9, but you shouldn't, and underscore and a few more, but you should keep them simple, right? In fact, use a convention. The convention that I've been using is called lower camel casing, right? So in lower camel casing, if you've got multiple words that represent your variable, the first word is all lowercase. The second word, first letter, is uppercase. Each subsequent word has all lowercase except for the first letter. Why? You can't use spaces, right? And so you need a way to break the words so that it's more readable. If I had done it like this, lower camel casing, right? Can you read that as well? Nope. But this is way easier, to understand, right? Because each word is offset by a casing convention. Yeah?
Why have the first letter lowercase?
It's a good question. It's because there is upper camel casing, right? Upper camel casing is used, but in different contexts. In C, we'll use it when we define our own variables, structures. Right? We'll use those as structure names and enumerated types later on, right? But we will use it. Why is it called camel? Humps. Camels have humps, right? So they're low, high, double humps, just one hump camel. I don't know what the difference is. I'm not a camelologist or whatever they are. Right? Okay. You can assign, the last thing I'll show you for next time is the assignment operator. And this is where we'll pick it up next time. Right? Variables hold values. You need a way, to get values into variables. So you use the assignment operator, a single equal sign. Let me go into code mode here. If I declare a variable int x, I can immediately, first of all, what value does x have right now? It's a mystery to everyone. Who knows? It's not defined by the C standard. It could be 0, 99 times out of 10, depending on the compiler, depending on the system, it will be 0. But you cannot rely on that. Right? It could have some what's called garbage value or dead beef. Dead beef is hexadecimal speak. It's just a placeholder value because we can create names out of A through Z. What words can we form out of A through F? Oh, we can form dead beef. All right, that's funny. Let's go ahead and use that as our convention for an uninitialized variable or uninitialized memory. So that name is stuck and it's dead beef. It could be 0. It could be some garbage value, whatever was left in memory the last time the computer used that chunk of memory. We don't know. So how do we get stuff into it? I can assign a value x equals 10. This is not math. Right? This is not a math of x is equal to 10. I'm saying take the thing on the right-hand side of the equal sign and put it into the variable on the left-hand side. That's the assignment operator. We're not testing equality. We're not asserting that x is equal to 10 or that is x equal to 10, right? We use different syntax for that, and that's what we'll get into next week. Okay? All right, any questions? Otherwise, remember your first hack is tomorrow. It is due on Monday at midnight. Your first 2 readings are due on Monday at 5 o'clock.